Another thing I want to quickly mention is 5c. So I have a function x z squared minus yz minus x cubed y is equal to 1. I want to compute partial z, partial y. Okay? Partial z, partial y. So the keywords about computing partial z, partial y, when you have a function which is written in the implicit form. Okay? The only thing about implicit is you don't have a formula of z equals a function of x, y, right? This is not explicit because you don't have the formula z equals anything. You can try to solve this cubic equation involving, you can try to solve this quadratic equation involving z. But the point is we are not testing you how well you know quadratic equations. Right? We're about taking derivatives. And this is, the keywords is implicit differentiation. So you want to design a function which is implicitly containing all the variables. Minus 1. And in fact, I have a 1 on the right hand side. You can name your capital F to be the left hand side directly. It doesn't really matter. Because when we take the derivatives, these constants are all vanishing. Right? It doesn't really matter too much. But to be strict to the formula, I design a new function. And then within this new function defined by capital F, partial z, partial y is going to be minus phi y and f of z. Okay? So it's a quotient of two partial derivatives. And then with a minus sign right here. So you take the derivatives about this function, they're all polynomial. So taking the derivatives is very easy, and I want to evaluate at a point of 1, 2, 3, you just plug in the number in the formula, right? So you compute the formula and then evaluating by plugging the numbers. Okay? So questions? Yep.
5b.
We can discuss afterwards. I'm only gonna talk about some common mistakes. So individually, you're always welcome to discuss with me about any other problems. Okay. So I want to quickly go through the very last question so we can discuss intervals. Okay. Number 8. Okay. So number 8, I have to take a certain responsibility as well. So this is the 6 points I delete from the total numbers because this problem is not very well received among you. So this is what I want to do. I want to find the closest point. So the point on the plane x minus z minus y plus z is equal to 4, which is closest to 2, 2, and 2. Okay? So I remember during the lecture, we discussed this question at the end of part of Wednesday. So we didn't go through the details of the computation. So this is probably one of the reasons you guys did not do very well on this particular problem. So that's one of the rationales I decided to exile this from the total points. So again, I want to find the distance between the points, no matter what point. As long as you have a point x, y, z with another point 2, 2, 2, at least you have to give me one formula, you know. Right? I give a lot of partial credits as long as you can write down something relevant. Okay? So regardless, I know the distance, if I want to name it, distance between a point and this point 2, 2, 2 is going to be equal to square root of x minus 2 squared plus y minus 2 squared plus z minus 2 squared. Because when we're talking about the closest, we're talking about distance between points. So at least you have to give me this formula, okay? And then I want to minimize this distance. In other words, I want to minimize this square root. And as we discussed during the lecture, minimizing a function is about finding the critical points and using a second order derivative test to see whether it is a minimal value or not, all right? So we have to use the derivatives. Taking derivatives about square roots is not it's okay, it's not difficult, it's just messy, right? It's complicated. I don't want to take the derivative for this function. But minimizing the distance as the square root is the same thing as minimizing a function x minus 2 squared plus y minus 2 squared plus z minus 2 squared. Okay? However, I haven't really used the condition that this point x, y, z is on a plane yet. Right? So I have to take advantage about that. Otherwise, there's nothing about minimizing this problem at all. You can simply choose x, y, z to be 2, 2, 2. You don't have anything. Right? So I have to use this condition here. In other words, this condition is an equation involving 3 variables. And I want to use this one to eliminate one of them. Right? You can choose your least favorite one. Doesn't really matter because we can do derivatives with respect to xy or xz or yz, right? Which one you dislike most?
Y.
Z is probably the one we usually do, right? So z is equal to 4 minus x plus y. So I can plug in this formula. So it's going to be x minus 2 squared plus y minus 2 squared plus 4 minus x plus y, then minus 2 squared. And then after I do that, I'm going to get a function involving only 2 variables. Okay? Now the problem is translated into a much firstly form. I want to find the critical point for this function and classify it or verify it. It is indeed a minimal value, right? And this is our best friend. The polynomials are indeed our best friend. The polynomials, you can do derivatives, you can do integrations. Most of the computations are very straightforward. So I need to simplify these squares, and in the end, I'm getting 2x squared plus 2y squared minus 2xy minus 8x plus 12. So this is the function I want to optimize in terms of finding the minimum value. Okay? So the keywords I'm looking for is critical points. So the critical point is x derivative is equal to 4x minus 2y minus 8 is equal to 0. And fy is equal to 4y minus 2x is equal to 0. So this is a system of 2 linear equations, right? So solving these 2 equations is pretty straightforward. So I'm getting x is equal to 8 divided by 3, y is equal to 4 divided by 3. And I can easily verify by second order derivative test such that this point is indeed the point where you can achieve a minimum value. All right? Because if I want to compute the second order derivatives, so fxx is equal to 4, fyy is equal to 4, fxy and fyx are both equal to 2. Am I right? So this is a positive definite matrix. The determinant is positive, fxx is positive. So this is indeed a minimum point. Right? So this is where the function will achieve the minimum point. However, I need to find this point on this plane such that it is closest to 2, 2, 2. I only got 2 values. The only thing I need to do is to complete by adding a z. Right? So z is equal to 4 minus x plus y is equal to 8 divided by 3. So the point which will be closest to 2, 2, 2 will be 8 divided by 3, 4 divided by 3, and 8 divided by 3. So that will be your answer. Okay? So in the very first lecture during the whole semester, I said the key thing is about how to identify the problem and pull out the correct formula. Okay? So some of the questions are pretty straightforward, like this one. I already asked you to approximate a function. So naturally, you are looking for the linear approximation. Sometimes the problem is not very clear what you need to do. Right? So you have to translate by identifying the problem. So this problem, identifying the end, is about a minimizing question or optimization question. In other words, I need to find the critical points, and that's about it. Again, I want to stress this. You don't want to throw away this test, okay? So after I give back your test, and also you can refer to the answer keys I upload on the Canvas. While your memory is still fresh, making sure you can do every single problem, okay? And also before the final, you pull out this tester in and go through the questions one more time and see whether you can do them, okay? So making sure all the questions are with your power. So is there any people who haven't got the test back yet? So we spent half an hour to talk about the test. Hopefully that will be helpful to you. So. So if you have any questions concerning the questions itself, problem itself, or grading, you're welcome to come to me. Okay? And I understand how important it is for 1 and 2 points. So I don't want to penalize you for my mistake. So if you find any arithmetic error, if you find anything you don't agree with my grading, do not hesitate to come to me. Okay? So I want to resume our discussion on the double integrals. Okay. So this will be our main theme for the following several lectures. So what we need to do is to compute double integral of a function with 2 independent variables on a region R. Okay. So we explained why this problem is significantly more challenging than the single variable calculus. The main reason is because you have much more varieties for the region, the intervening region in R2. Right? In R1, the only intervening region is an interval. In R2, the intervening region can be a rectangle, can be a disk, can be an ellipse, can be anything. So this is the main complexity. The other explanation about this double integral is in terms of a volume. So this integrating region is in R2. For instance, if this is x1, so this R as integrating region will be in this plane, xy plane. So let's say this is my integrating region. Okay. And the function fxy will be a surface. Z is equal to fx1. Okay, so this double integral is indeed talking about the volume under the surface above the integrating region. Okay, so this is equal to the sine volume under Z is equal to fxy above. So this is another explanation of a double integral in terms of the sine volume. By sine volume, the only thing I'm talking about is if the surface is below xy plane, you're supposed to count the volume as negative. If the surface is above xy plane, then we're supposed to count the volume as a positive volume, right? Just as we did in the single variable case. And I'm planning to go over 5 different types of this intervening region, and we already covered one of them. So the first one is so-called a right angle. So right angle is defined as x is bounded by AB, y is bounded by CB. Okay, so a right angle region will look like a block rectangle. So this will be the region up, and AB Okay? So once we identify the rectangle as the integrating region, we have a way of computing double integral. Right? We have two different routes to go compute this double integral. Are you with me? Right? So either it is equal to CP AB fxy, I do the integration with respect to x, and then with respect to y, or I switch the integrating order to get integrating inside with respect to y and outside with respect to x. So if your integrating region is a rectangle, everything is nice and easy. You can write down your double integral as two single integrals. Okay? And you can do the single integral either with respect to x first or with respect to y first. Okay? And the other thing is, as long as you write down your double integral as two single integrals, evaluating the middle integral, the interior one, will eliminate one of the variables. Okay? So if you still remember what we did last Wednesday, we write down it as a two single integral. So after we evaluate the interior integral, we eliminate the variable x. All right? And then, as long as you've done that, the outside will be a single integral with respect to y only. Okay? You can switch the order. It's just a single variable calculus. Everything is nice and easy. So today I'm going to introduce two new types of regions. One is so-called y simple region. The other one is called x simple region. Okay? So the y simple region is in the form such that x is bounded by two numbers, y is bounded by two functions. And in x simple region, y is bounded by two numbers, x is bounded by two functions. Okay? So before we actually discuss about these regions, I have one big announcement here. Okay, this is absolutely the fundamental knowledge of going through the whole double integral and the triple integral. You definitely have to make sure you know how to deal with this x simple region and y simple region. Okay, so this is so crucial, such that you don't want to mess up this part. Okay, so let's begin.